Okay, we're going to do another hypothesis testing procedure for this video, but we're going to make things a little bit more realistic, and that is a little bit more complex. So if you're not comfortable with the 5 steps of hypothesis testing, you'll need to review the previous 1 or 2 videos because you need to be comfortable with that process for me to then make it a little bit more complicated to reflect reality, okay? And for this example, I'm going to use sort of a physical therapy example, and let's suppose that you're a physical therapist specializing in the elbow, okay? So movement of this joint, right? What's nice about movement of the elbow is that we can measure how well you can move in a quantitative way by just looking at this angle here, okay? So that would be 0, and that would be 90, okay? And that would be 45, okay? So we're just going to measure the angle of movement, the range of motion there. And let's suppose that normally when someone comes in for treatment on their elbow, that the normal therapy after 2 weeks of working with the person, let's say on average, they improve by 20 degrees, right? We're going to measure the movement in degrees. And let's say that some young physical therapist has an idea that might improve this level of improvement after 2 weeks, because this is a joint, and one of the things that is going to affect the movement of that joint is inflammation in the area, right, in the tendons or ligaments. And so this physical therapist is making a hypothesis that if we treat people right before therapy, let's treat them with anti-inflammatory drugs, the NSAIDs, that is non-steroidal anti-inflammatory drugs, okay? So let's suppose that if we treat them with a high dose of NSAID just prior to their therapy, maybe this would help us improve this normal improvement that we see, okay? Now from that information, you should be able to generate our hypotheses for this research, okay? So the null hypothesis would state that the people who get NSAIDs will show the same improvement as people that get normal therapy, okay? That is, the NSAIDs won't make a difference. Or we can write it like this: the NSAIDs, the improvement after 2 weeks is going to be 20 degrees, okay? That should be relatively straightforward. This is the null. Our research hypothesis, really, what will be alternative to the null, is that when we use NSAIDs, we're going to see that there's going to be some difference compared to the normal treatment. Or, alternatively, we can say if we give the NSAIDs, then we're going to see improvement of something other than 20 degrees, okay? Again, I'm going to do this as a non-directional hypothesis. I certainly want to know if giving NSAIDs decreases performance, but hopefully it'll increase the effectiveness of the therapy as well, okay? Step number 1. Step number 2, let's talk about our alpha level. We're still going to keep that at 0.05%. That means we have a 5% chance of making a type 1 error, but that's okay. That's a pretty low percentage, okay? And then this corresponds to a z-score of plus or minus 1.96. Pretty straightforward, okay? So far, so good. And so then we need to collect some data. I'm going to erase step 1 here, assuming that you have that in your notes so we can go back and look at it. Step 3, let's collect the data and do the analyses, okay? And let's suppose that these are let's suppose that we recruit 9 people for our study, okay? And that these are the outcomes for those 9 people. So this is how much they improve. 18 degrees, 23 degrees, 28 degrees, 20 degrees, 25, 31, 30, 28, and 16. Okay? Notice that there are a couple that actually got less than what's normal. There's one person that got about the same, but there's a bunch that do look like they have more improvement. Let's do our analysis. Okay? So first we should get the mean for this group. And so if we add all these together, let's do this, okay? 18 plus 23 plus 28 plus 20 plus 25 plus 31 plus 30 plus 28 plus 16 equals 219 divided by 9. Okay, so the average for this group is 24.33 degrees. Okay? So far, so good. So let's do our z-score. We're going to compare this. Well, right here's what the z-score looks like. So we're going to compare 24.33 to 20 divided by the standard error for the group. So, oops, what is this here? Okay. If we had this value, could you do the rest of the problem? If you answer yes, because you're comfortable with the 5-step procedure, that's awesome. If I gave you this and you said you couldn't do the rest, then you need to go back to the other videos and get that figured out, okay? But the reason that things are more complicated with this example, and in fact more realistic, and reality can be very complicated. So far, I'm giving you information, but sometimes you don't have that information. And so we need to develop procedures to deal with that. So I'm not going to give you this information. Okay? Because in reality, we rarely have that information. And so now we need to figure out what to do. Okay? Again, I'm going to ask you this question. If you had that information, I'm assuming that you could do the rest of the problem. You know, get to step 4, get to step 5 with the conclusion, and so on and so forth. So we're going to work on making a guess for this value. Okay? We're going to make an inference about this value. Once we get this, then we're going to do the procedure like we've done before. So, like I have said multiple times, let's think this through. First of all, we have to figure out what this is, okay, what that symbol stands for. I know that you know it's standard deviation, but standard deviation of what, okay? Well, this is, remember, this is the group that gets treated normally in the PT clinic, okay? They have an average of 20-degree improvement, but not everybody improves at 20 degrees, right? Some people are above it, some people are below it, so on and so forth. I mean, I'm assuming that you can picture that curve in your mind's eye. Okay? Now, this is of the people that are getting the normal therapeutic intervention, but really we don't have that information. If we did, we could then put it in here. We don't have it, okay? So the question is then, do we have any indication on this whiteboard of any measure of variability for people's elbow movement? Do we have some sense of the variability of people's elbow movement? And the answer is yes, we do, because these people treated with the NSAID, remember this is the NSAID group, they're showing some variability, right? But remember, this is the variability of the normal therapy group. This reflects the variability of the NSAID therapy group. This is the normal therapy, this is the NSAID. So you might think, well, we can't use this variability to make a guess about this. But we need to remember some of the stuff we learned from previous videos. And that is, there's two possibilities. I mean, if we fail to reject the null, ultimately, if we fail to reject the null, we're saying there's no difference in the NSAID versus the normal therapy, then these people represent normal therapy, right? If there's no effect of the NSAIDs, this would represent normal therapy. So in that case, we could use this to make a guess for this, all right? So if we fail to reject, then this really represents normal therapy people. If we reject the null, and we say that the NSAID cause and effect, then these people came from a different population than what we're talking about here. This is the normal therapy population. This is the NSAID group. But, remember what we talked about in the previous video. If a treatment exists, it's just pushing that curve up or down, but it is not changing the variability of the curve. Very important point here. I'm going to say it again. If there is a treatment effect, it's just moving the curve up or down. That is, it changes the mean, but it doesn't change the standard deviation. Therefore, even if there's a treatment, this variability should somehow represent what's going on here. Okay? If we fail to reject, this is just like the normal therapy, folks, and we can use it. But even if we reject the null, and this comes from a different population, we're assuming that the population, that the curve was just pushed up or down. That is, it affected the mean, but not the standard deviation. That's an extremely important point, and it allows us to do what we're going to do next. So make sure you think about that, replay that, and listen to it. If there's no treatment, then we can use this to make, we can use the variability here to make a guess about this. If that's a little bit more intuitive. But even if there is a treatment, even if this comes from a different population, we're assuming that the mean of that population is different, but the variability is the same. Aha. So that's a good thing. So now what we need to do is find the sum of squares for this group, the NSAID group. And here's the formula, so you don't have to go scrambling for it. But you'll need to be able to do this, and I would recommend pausing the video right now to calculate the sum of squares, because I'm just going to give it to you, but you certainly need to have practice with this. Remember, this one we're squaring each number first, 18 squared plus 20 squared, plus 30 squared, plus 23 squared, okay? This one, we add the numbers together, then square, divide by n, okay? So see if you can calculate that, and I'll pick up from there. Okay, so sum of squares here. Let me give you the expanded version. 5563 minus 5329. Just in case you don't get the correct answer, you may be able to see where you're wrong. So here's our sum of squares value. Okay, there's the sum of squares value. Of course, I don't want sum of squares. I want the standard deviation. So standard deviation is equal to sum of squares divided by n. Take the square root, which is 234 divided by 9. Don't forget to take the square root, okay? Don't forget to take the square root. 234 divided by 9 equals, take the square root. So 5.10. 5.10 is our standard deviation for this group of 9 numbers. Okay? It's the standard deviation for this group of 9 numbers. Okay? So, once again, because there's 2 possibilities. If we fail to reject, then this should somehow represent the population of people getting the normal therapy. But even if we have a difference, even if we end up ultimately rejecting the null, we're assuming that the population just shifted up or down, but the variability remains the same. Okay, that's the important concept to remember. So we should be able to use this to make a guess about this. Okay? And if we get this, we can do the rest of the problem. Right? That's what you told me. All right. Well, we do have a problem. Another problem, okay? And here's the deal. Remember when we were doing the sampling distribution of sample means? And I told you the reason that I took so much time to do that example, right, pulling the blocks out of the canvas bag, the reason why I took so much time to do that is because, number one, it's an important concept, central limit theorem, but also we need to remember the procedure now, again, the actual, like how this happens. So we're going to do a sampling distribution again, but now we're going to do a sampling distribution of sample standard deviations. Remember before we did a sampling distribution of sample means. Now we're going to do a sampling distribution of sample standard deviations. And you're like, what the? Well, listen, here's what we're going to do. I got my canvas bag. I'm going to go in, I'm going to grab a sample, let's say a sample of 9, okay? I'm going to go in, grab a sample. I'm going to calculate the standard deviation of that sample, just like I did here. And I'm going to plot that on a curve. Okay? Now instead of m's, I'm going to have standard deviations. Okay? I'm going to plot this value on the curve. I'm going to put the blocks back in, go in, take out 9 more blocks, calculate the standard deviation. It's going to be different than this. I'm going to plot it. Okay, put those 9 blocks back in, take out another sample of 9. I'm going to calculate the standard deviation and plot that. Okay, I'm going to keep doing it 1,000 times, 10,000 times. So it becomes a sampling distribution of sample standard deviations rather than a sampling distribution of sample means. Okay, take a minute. Go in, take a sample, calculate the standard deviation. That becomes 1 block in our distribution. Take out another sample, take out another sample, take out another sample. This is what we would call standard distribution of sample standard deviations. Okay. Can we picture that in our minds? Now, whereas when we did the sampling distribution of sample means, what we found was the mean for the sampling distribution, mu sub m, ended up being equal to the mean of the distribution from which the samples were taken, right? The overall sampling distribution of the means was equal, the mean of that distribution was equal to the mean of the original. With standard deviation, it's a little bit funkier. And what we find is that the standard deviation, I'm going to say this slowly and I'll say it again. Standard deviations from samples tend to underestimate the standard deviation of the population from which the samples were taken. I'll say it again, and I'll say it more slowly. But I want you to think before you write, okay? The standard deviation of a sample tends to be smaller, tends to underestimate the standard deviation of the population from which it came. So when we talk about that canvas bag, there is a certain standard deviation in that canvas bag. Samples tend to be a little bit smaller than the standard deviation of what's in the bag. Okay? So this ends up being an underestimate of this. Okay? This, for this sample of 9, tends to underestimate the population variability. And that's called a biased estimate. It's biased because it underestimates. Okay? So we need to do an adjustment. And by the way, this information is the information that we skipped from chapter 4. So in the textbook, you need to read section 4.5 in chapter 4. That's where this is covered. So this is going to underestimate our population standard deviation. Okay? And so, right, how do we get this? Took sum of squares divided by n. Okay. So what we're going to do is we're going to make an adjustment. This is a bias estimate. I mean, I tell people, this is like if you went to your bathroom scale and you weighed yourself, but you always know that it's 2 pounds less than what you really weigh. That's a good scale. No, it's not a good scale because it's not accurate, right? Then you need to make an adjustment, right, when that happens. So we're going to make an adjustment. This tends to underestimate. This is called our bias estimate of sigma. And let's make sure we keep the symbol straight. This is the sigma for these 9 numbers. This is the standard deviation for these 9 numbers. But what I want to do is I want to guess what the standard deviation of the entire population is. Not just 9. You know, when we talk about a hypothetical population, it's going to be an infinite number. So we need to make an adjustment. And here's what we're going to do. This is an underestimate, so we need to adjust to make this bigger. So we're going to do the standard deviation divided by n minus 1, then take the square root. Different formula, so we're going to use this symbol, lowercase s, okay? And what do we have for lowercase s? Well, we have 234 divided by 8 now. Take the square root, okay? 234 divided by 8, then take the square root. 5.41. Notice it gets bumped up a little bit, right? It gets bumped up. We've adjusted. We know that this underestimates the population standard deviation. So we subtract 1 in the denominator. That will end up increasing it. This formula is used to make an unbiased guess for population sigma. Okay? And I always tell people, can we get rid of this for a moment? I need more space here. I always tell people, S is our guess. S is our guess. S is our guess. Okay? S is our guess for the population standard deviation. S is our guess. Now this can be confusing, right? Because, wait, what's this? Well, we use that term because this is the standard deviation for those 9 numbers. Remember the arbitrariness of sample versus population. If we had those 9 numbers, this is the standard deviation of those 9 numbers. If I gave you an exam and I said, what's the standard deviation of those 9 numbers? This is your answer. But what we want to do is we want to ask, well, do those 9 numbers represent the population standard deviation? And the answer is no. This is a biased estimate. It tends to underestimate the population. And so we make this adjustment, make that number bigger by subtracting 1. This is called the unbiased estimate for sigma, our unbiased guess. Okay? So I'm going to do this. I'm going to do this. So this is our unbiased estimate for population. Okay? It is S, sum of squares, divided by n minus 1. And this n minus 1 is also called the degrees of freedom. And so we can also write this like this. Degrees of freedom is the number in our sample minus 1. Degrees of freedom is the number in our sample minus 1. Okay? I mean, it's probably the simplest formula, right? Degrees of freedom equals n minus 1. But it's a fairly complex concept. I'm not going to get into it right now. Just know that degrees of freedom is the term. It means n minus 1. Okay, we can talk about that a little bit more later if we want. Okay. So what we're saying here is our guess for sigma is going to be 5.41. That's what we're going to use. But we're going to use this symbol. Instead of sigma, we're going to use little s. And the reason for that is because it is a guess after all. It is a guess after all, okay? Sigma means that you have that information, the population parameter. This means that you're guessing for it, okay? Now, another source of confusion, and I remember very well taking this course, and here's another place where I think the textbook falls a little bit short in terms of explaining this. In Chapter 4, they will say, this is the standard deviation for a population, and this is the standard deviation for a sample. I do not believe that's an accurate description of these two things. Like, if I have those 9 numbers, I'm going to tell you right now the standard deviation is 5.1. Those 9 numbers have that standard deviation. Because if I'm just considering those 9 numbers, right, as a population, then I just do this I just do this. If I'm using those 9 numbers and I want to make a guess for what's happening in the population, then I use this. So it's not the case. I remember raising my hand with my professor. And I said, So the standard deviation changes because you change the name of the group of numbers, sample versus population. And I don't remember his response, but I wasn't satisfied. And until I, took more statistics in graduate school and taught this course, I'm like, oh, it's not really, if you call it a sample, it's this value, and if you call it a population, it's this value. Those 9 numbers have a standard deviation, in this case 5.10. But if you want to say, well, suppose it was a sample from a larger population, then what would be your guess? Right here, I use my unbiased estimate. Okay? And again, if you have questions, drop me an email, okay, or we can Zoom or whatever. So S becomes our guess for sigma. You told me when we started this video, if I gave you this information, you could do the problem, right? And the answer is yes. So if I'm using this to sort of replace this, then what do I do next? Remember, in our Z formula, it's not sigma, it's sigma sub m, sigma sub m. And so I need to go from sigma to sigma sub m, and how did I do that? This is just our standard central limit theorem step, okay? Yeah, folks, it gets more complex, okay? I don't know what to say. That's the nature of the real world. This is what we have to do, okay? So what I'm going to do here, this central limit theorem step, I still need to do, right? Once I gave you this, then there's one more step before we go here. Once I give you this, there's one more step, okay? But now we have an estimation for sigma, not sigma itself. So we're going to do an estimation Everybody with me? Same formula, different symbols. People sometimes gets freaked out by that because it's like, how can it be the same formula if it's different symbols? This is just telling me that I'm deriving this from an estimated sigma, not from the actual sigma. That's all this is telling me, that it's derived from a guess for sigma, not the actual sigma. Okay? So now we have two steps. Try to conceptualize it like that. We got to estimate sigma. That's one of our steps. And then we'll do the same old central limit theorem step here, okay, by doing this. So this is going to be 5.41 divided by the square root of 9. Now, sometimes people ask me, and it's a good question, I think it's a great question, do we need to subtract 1 from this? The answer is no. We didn't do that before, right? So we're not going to do it now. You treat S as if it was sigma. Now, we did this with sigma, okay? Another way to think about it is we've made our adjustment here. We don't need to adjust again. It's almost like, if you guys remember, or well, it still happens, but I remember as a kid when I saw some track events where they have an oval, right? The racers go around the oval. But they start in a staggered fashion at the beginning. And, when you're a little kid, you're like, well, that's not fair. The person, in the outside ring gets a head start. Well, it's because the outside ring is, if you have to stay in your lane, the outside ring is slightly longer than the inside ring. And so they make up for that by staggering the start, okay? Once the runners are started, that is, once that adjustment is made, it doesn't get made at the end again. So we make the adjustment here with degrees of freedom. Then we just go to here. We've already made the adjustment, okay? Does that make sense? All right. So this now becomes, we use this for our guess for sigma. We use this to do our central limit theorem step. Make your guess for sigma, then do central limit theorem. Then we'll be able to plug in here. So this number is 5.41. Oh, let me do this. 5.41. I know the square root of 9 is 3. So it's 1.80. With an estimated sigma of 5.41, the central limit theorem standard error is 1.80. So that's what goes in here. Okay. Now, before we go any further, let me show you the symbol here. This is actually going to be our t-test. Some of you may be familiar with that term. Instead of a z-score, the t-test is our sample mean compared to our regular therapy or normal or untreated or whatever you want to call it, divided by S sub m. Notice this formula and this formula. Same formula, different symbols. Z is used when you're given the mean and the standard deviation. T is used when you have to estimate the standard deviation. Estimate it, then give it central limit theorem treatment. Okay? Same formula, different symbols. This is saying that we have an estimation for sigma, not the actual sigma. So this becomes a t-test, not a z-score, because we don't have sigma. And now we can get our value for t, and the value for t here is 2.41. 2.41 for our value of t. Okay? Now, so this is step 3. This is step 3. We've done our analysis. The t-test is the z-test when you estimate for sigma. Okay? Same formula, different symbols. It's based on the fact that we first needed to get an estimate for sigma, then turn that into standard error, and then do our value. Okay? All right. We need to decide whether we're going to reject or fail to reject. And I'm going to show you a graph here. If this represents the z distribution, where we would have a z of 1.96 and minus 1.96, remember that corresponds to our alpha level of 0.05. With a t distribution, the t distribution tends to be a little bit more variable because we're making a guess for sigma instead of having that value. And so relative to the z, the t ends up being a little bit more flattened out, right? If it's more variable, it's more spread out. So this would be the t distribution, okay? If we use a t of 1.96, are we going to have more than 5% in the tails, less than 5% in the tails, or 5% in the tails? If instead of a z of 1.96, we use a t of 1.96, we would have more than 0.05 in the tail, less than 0.05, or 0.05. Well, if we're squishing this down and it's more spread out, then we're going to have more than 5% in the tail. That's not cool because I want to keep my probability of probability of type 1 error, which is equal to alpha, I wanted to keep it at 0.05. So what we're going to do is we're going to move the critical value out a little bit, So it's going to be greater than 1.96, less than minus 1.96, but not too much, okay? And in fact, the adjustment that we need to make is less with the more subjects that we have. That is, the higher our degrees of freedom, the more the t distribution approaches the z. If we have, and this should make sense, the more people we look at, the closer we're going to get to making a good guess for the population. Okay, this is heavy stuff, folks, heavy stuff. All right, well, here's what we're going to do. Instead of using z, then, we're going to use a critical, we're going to call it critical t-value. And in parentheses here, I'm going to list the degrees of freedom for our example. Since we use 9 people, the degrees of freedom is 9 minus 1, so it's 8, okay? And we need to find out what is the critical value, that is the cutoff, that we're going to reject or fail to reject the null. If you look in the back of the book, after the z table, after the unit normal table, there's a 1-page t-table. And I've just taken an excerpt from that right here, okay? It's the t-distribution. Along the left-hand column, you'll find degrees of freedom, okay? Now, the top portion of this table, you'll see all sorts of different proportions. It'll say proportion in 2 tails combined. Well, if we look at the 2 tails combined, what do we want? We want 5%, right? We want 5% in the 2 tails. So look at that column. Look at that column where it says proportion in the 2 tails combined, 5%. And you will see a whole bunch of critical t-values. If we have 6 degrees of freedom, the critical t-value is 2.447. 7 degrees of freedom, critical value is 2.365. 8 degrees of freedom, well, that's what we have. Our critical value, 2.306, okay? That is the equivalent of 1.96 for our z. Remember, I said we have to move this out a little bit, okay? So instead of 1.96 and minus 1.96, we have 2.306, positive and negative, okay? Now, don't just look up the information here. There's a pattern that I want you to see in this table. It allows you to understand this better if you see the relationship between degrees of freedom and the proportion in 2 tails. Look, going down, going down, going down, going down. If you look at the very bottom of this table, you'll see that if we have an infinite number of degrees of freedom, 1.96. What they're saying in this case, an infinite degrees of freedom means we must know the population. If you know the population, then the t-test becomes a z-test, right? You're not really making an inference. You are using the actual standard deviation, okay? If we had 120 degrees of freedom, we're at 1.98. So as you decrease the degrees of freedom, things get bigger, or as you increase degrees of freedom, that critical value gets smaller. Okay? That's from your book, and you just look up the critical value. So, we have an observed value of t, that's 2.41. Compare it to the critical. So here's our NSAID group. So we're going to what? What's going to be our decision in step 4? Our decision in step 4 is reject the null. Okay? I don't think that the NSAID population and the normal therapy population have the same mean. And what I'm saying here is the NSAID is helping to improve. So I want to do step 5. It appears that administration of NSAID before therapy significantly improves, what do we want to call it, recovery? Same thing. I want people to know this is not my opinion. I collected data. I did the statistical analysis. And here's what I'm going to do. T, and I'm going to put 8 degrees of freedom. That's standard reporting. Equals 2.41. Okay? Please pay attention. I'm not reporting the critical value. That's just my reference value. I'm reporting what I have seen in my research. Because some people will pop this in down here, and I'm like, no, that's incorrect. You won't get full credit. You want to report your data. And then semicolon, P less than 0.05, okay? Period after the parentheses. The t-test is used when you're not given this, when you have to estimate it. And that is it's the most common thing. You're not typically given this information, and so you need to estimate it. Get your unbiased estimate for sigma, that's known as S. Then do your central limit theorem, right, where you take little s divided by the square root of n, that gives you S sub m. That's what the t-test is. So the t is this. Here's your research sample. Here's the mean that you want to compare it to. And then here's our standard error that's based on an estimate for sigma rather than sigma itself. So, wow, chock full of information, this video. Thank God you can watch it again if you need to. We will do another example of a t-test in the next video. And what I'll do is I'll go through all 5 steps and annotate basically what we talked about in this video, but in less detail. So, I would recommend watching this again. I don't know what to say. Unless you really got it, you might want to watch it again. So next video, we'll do another example.